This video is going to illustrate the Gage repeatability and reproducibility studies that one can do within the QC Pro Gage management software. We'll use a numerical example taken out of the Automotive Industry Action Group's Measurement Systems Analysis reference manual. And to do that, we'll start by going into transaction. And we've already set up a gauge here, so we'll just set up a new transaction. And the type of transaction that we're going to be doing is not a calibration, but rather a measurement systems analysis, MSA. Let's say the actual MSA study was done on the 16th of January 2018. And let's say the person, the quality analyst who's going to be overseeing this study is, let's say it's Bill. And we can put in some descriptive information related to this, but we'll just leave that blank for now. We can also assign a part ID that's going to be used for this particular study. So let's say the part ID is, I don't know, some number like. And the characteristic that we'll be measuring is going to be, let's say it's thickness. So we'll go down to thickness. This is all optional, by the way. You really don't need to enter this, but for the purposes of this illustration, we will. The unit measure, we'll just leave that blank. And let's say the tolerance on this is 20, whatever the units are that we're measuring in. Now, we're going to be doing the type of measurement systems analysis that we'll be doing for this video will be what's called the GRR, Gauge Repeatability, Reproducibility, and the method that we'll be using is something called average and range, which again is taken straight out of the AIAG reference book. So we'll stick to that. The other types of MSA studies that one can do are illustrated here in this drop-down list, and we'll talk about those in a separate set of videos if you're interested. So we picked that, and now the illustration that we're going to be showing you here is one that has 3 operators, 3 people doing the measuring. They'll be taking 10 parts, and the number of trials, the number of times they're going to take, for example, part number 1 and measure it will be 3 times. So this is sort of the preliminary setup for this MSA study. And we'll just click on the save button up here to save things, and now we'll go into the data entry screen for the Gage R&R study. Now we have color-coded the columns so that the blue columns here, the first 3 columns here are in blue, which would represent operator number 1. So let's say operator number 1 was Don. You don't have to put in a name here if you don't want to, but we will, just for illustration purposes. And then the green columns, the next 3 columns will be green, and that represents operator 2. Let's say that happens to be Linda. And then the remaining 3 columns will be for the 3rd operator, and let's say that happens to be Susan. Okay, and then we'll enter a few readings here just so that you see how that's done, but we're not going to actually enter all the readings. We'll come back and actually have that pre-populated in a moment. So for example, for the first trial, we have 10 parts that we're going to be looking at, and for appraiser number 1 or operator number 1. So Don will measure those 10 parts. And so, for example, the first measurement would be 0.29 for part number 1, trial number 1. And for part number 2, it's minus 0.56. And for part number 3, trial number 1, it's 1.34, and so on. You get the idea of how to enter data. So we'll just kind of stop here for a moment, and then we'll continue with the remaining set of data already populated in here. So now we have the data set within the data entry grid for all trials, for all operators. And at this point we would click on the OK button and then click on the Apply button, which saves it in the database. So now we can have a look at the various reports. We'll look at the data sheet, and you get a little pop-up here saying that the ranges are found beyond control limit, or one of the ranges anyhow. So what that means is if we look at the data sheet, we can see for trial number one, we have, sorry, for part number one, we have 3 trials, and we see that for each of those parts, we've calculated an average of those 3 trial measurements. So that would be the average for part number 1, for operator number 1. And we've also calculated a range for part number 1, operator number 1, or appraiser A. And so the range would be defined as the largest measurement, which happens to be 0.64, and the smallest measurement is 0.29 out of the 3 readings. And if you take the difference between the 2, that gives us the range. Now, we've also calculated, in addition to these averages and ranges, we've calculated a grand average of these averages for appraiser A, and we've also calculated an average range for these individual ranges for appraiser A. We've done that for the remaining appraisers as well. And so ultimately we end up with a average of averages, which would basically be average for appraiser A plus the average of appraiser B plus the average of appraiser A, and we add them up, divide by 3, and that gives us the average of the averages for the very first part for the 3 operators. And we would then be able to get the average of averages by adding up these 10 averages, and that gives us the average of averages, which is notated as X double bar. We can also get the ranges, or the range for parts, by looking at these averages and taking the largest value, which is this number here, and subtracting from that the smallest average, which is this. And if you work out the arithmetic, this is the what's called R sub P, or the range for the parts. And we can also calculate R double bar, which is the average of average ranges, and that works out to this number here. And the X bar difference would be the largest average minus the smallest average, which works out to this number. And the upper control limit is calculated by taking the R double bar, which is this number here, and multiplying it by a constant. And when we do that, we end up with this value here. So, I mean, all of these calculations are actually described in the AIG reference book, so I'm not going to go through it in detail. But just so that we finish this particular part of the data sheet, we've calculated an upper control limit of ranges of this number here, 0.8816. So if we kind of look through these ranges, we see that most of them are below that upper control limit. But for appraiser B, we see that there is a range here, 1.02, which is beyond the upper control limit of ranges. So what that's telling us is there's some anomaly that's occurred, which we have to have a look at. In other words, all the other ranges are below the upper control limit, so statistically there is no significance that we have to be aware of or concerned about. But this one seems to be beyond the natural variation for ranges. So the question is why that happened. Now, it could be for real, or it could be we maybe wrote down the number incorrectly for, let's say, a measurement, or it may be we did the measurement incorrectly by not putting the part in a proper way. Whatever the case may be, we need to look at that before we continue the study. And so that's sort of the guideline that you saw a moment ago, the pop-up that said there's a range or range, you want more than one range if beyond the upper control limit. However, we're not going to adjust these measurements. We're just going to leave it alone. And we're just going to follow the AIG reference numerical example and just leave it in there. So that's the data sheet with all the data measurements already populated in here. Next thing we'll look at is, let's say, the Gage GRR Analysis. Again, we're going to get that pop-up, which we'll just ignore. And so this reflects, we've transposed from the previous data sheet the R double bar, the X bar difference, and the R sub P, the ranges for parts. And we use this information in our calculations for the various components of Gage GRR. So for the repeatability, which is the error due to the measuring tool itself, sometimes called equipment variation, we do the calculation. We find that to one standard deviation, this is the value that we're getting, 0.20188, whatever the units are that we're measuring in. And for the appraiser variation, we kind of plug in the numbers and we get 0.22963 for the standard deviation for reproducibility, which is the operator-to-operator variation, or the error due to in measuring due to the people, sometimes called appraiser variation. And then if we combine the effect of both repeatability and reproducibility, we end up with a number that's shown here, 0.30575, which is one standard deviation in whatever units of measurement we're measuring in. And then the part-to-part variation, the standard deviation associated with the actual manufacturing of a part, can be derived from the raw data that we've entered. We're basically using the R sub P that we got from that previous data sheet, the range due to the parts. And when we work out the arithmetic, it comes out to 1.10456. So that's one standard deviation due to the parts, the variation associated with parts. And the total variation would be the Gage R&R standard deviation combined with the part-to-part variation. So when you kind of plug all that in and work out the arithmetic, this is what the total variation is in the overall system. And we're going to use this total variation value in our calculations. So if we kind of scroll back up to the top here, if we take the repeatability standard deviation, or the equipment variation standard deviation, and we divide that by the total variation and multiply it by 100, it gives us this value here. So we're saying that of the total variation, roughly 17.61% is due to the equipment component of measurement error. And if we do a similar thing for the appraiser variation, we take its standard deviation and divide by the total variation and multiply by 100, we get this percentage. The Gage R&R, which is the combined effect of both equipment and people, if we would be taking this number here, this standard deviation, dividing it by its total variation standard deviation, it comes out to this number here. And just to complete the story here, we'll calculate the percent variation due to the actual parts being manufacturing. So that's this standard deviation divided by the total variation, which comes out to this percentage. And finally, we calculate something called number of distinct categories, or NDC, which is the part-to-part variation, divided by the error due to measuring, which is termed Gage R&R. So the standard deviation for Gage R&R is in the denominator, and that comes out to be approximately 5. We would like the NDC to be 5 or bigger, and so since we're, I think it's 5 or 4, one of those numbers. In any event, we get an analysis of this or a guideline of this by the statements that are made down here. Since the number of distinct categories is greater than 4, so we have 5 here, so that's acceptable. And since the Gage R&R is between 10% and 30%, the Gage R&R may be acceptable based on the importance of application, cost of measurement, device, etc. So ideally we'd like the Gage R&R to be less than 10%, but I guess that's hard to come by many times. So between 10 and 30% is sort of an acceptable range, depending on what it would cost to improve the measurement system. For example, if it cost $1 million to improve the measurement system, it's probably not cost effective. If it's more than 30%, if the Gage R&R as a percentage of total variation is more than 30%, that obviously is, not obviously, but according to the Measurement Systems Analysis Reference Guideline, is not acceptable, and you'd have to sort of deal with it. So this is it for the regular way of looking at Gage R&R, and we'll just kind of close this report out. The other thing we can look at is the analysis based on what's called ANOVA, analysis of variance. Analysis of variance is a finer method of looking at the components of variation. And specifically, the thing that's missing from the regular way of doing Gage R&R studies is the possibility of some interaction between the people doing the measuring and the parts that they're measuring. So, for example, if you're measuring a very soft thing like maybe leather or something, and you might have an interaction between how one person would measure that piece of leather and another person might measure it. Or if it's a very big part and you have short people or a tall person and a short person, you may have some interaction between the people and the part that's being measured. So to handle that, we calculate the possibility of an interaction between people and parts, and if there is that possibility, then we have to take that into account. And you would never get that out of the regular way of doing a Gage R&R, but through ANOVA you can get that information. So the first thing that we calculate in the ANOVA table is to see what's important and what's not important relative to variation. And without getting into detail here, I'll leave that to you having a look at the AIG reference book. We find that for the appraiser component of variation, we calculate something called an F ratio, which is basically the ratio of variation due to appraisers, something called sum of squares, divided by the total variation. Sorry, my mistake. It's the mean square value divided by the equipment variation or the error variation. And when you work out the arithmetic, it comes out to be 34.44. Now, the bigger this F ratio, the more likely it is that that component that we're looking at, that source of variation, is an important factor. So at this particular level of significance, at the 5% level of significance, we're saying that the appraiser component contributes significantly to the overall variation, as do the parts. If we calculate the F ratio for parts, we take this number and divide it by the error component, and it comes out to be a large number, 213.52. So these two components are very important sources of variation at the 5% level of significance, statistical significance. The appraiser by parts, in other words, the interaction between people and the parts that they're measuring, is a small F ratio. So that's just telling us that really there is no significance between people doing the measuring and the parts that they're measuring. There is no interaction. So we really don't have to do ANOVA in this particular numerical example because it's not a factor. And if we kind of go a little further down here in the report, using the ANOVA approach, we can calculate things like repeatability and reproducibility to one standard deviation, just like we did in the previous approach. And we can also have the variance components, and we can calculate the percent of total variation just like we did before. So the repeatability or equipment variation would be the standard deviation associated with the repeatability divided by the total standard deviation. And so that works out to 18.4, which is not a whole lot different than the previous approach. And what's interesting is the appraiser by part. When we set that to 0, there really is no components due to the appraiser by part in the overall Gage R&R study for this numerical example. We can also have a column which looks at the percent contribution, which is basically the variance associated with, let's say, repeatability divided by the total variance. That's where this number comes from. And the number of distinct categories, just like in the previous set of calculations, is approximately 5, which is a good number. And so we get the same sort of results as our regular standard way of doing Gage R&R. NDC is acceptable, Gage R&R may be acceptable, depending on cost of getting better equipment and so on. And that's pretty much it for the analysis portion of the software for Gage R&R. Now, the one thing that and by the way, you can also get a blank sheet out of this thing if you want, just to record all the information, but that's up to you if you want. The other approach is to compare not against the total variation, but to compare against your tolerance band on the part that's being measured. So it is correct, or it is valid to do that if you wish. According to the AIAG Measurement Systems Analysis book, you would take your tolerance band and you would divide it by 6 to sort of put it in the same framework as the standard deviations that we're dealing with here in the approach that we just looked at. So just to illustrate that little possibility of using your tolerance band instead of total variation, we'll close this transaction detail out. And we can see that we've got in the transaction history, we've got our long, or what used to be called long, it's really the average and range approach, and the date that we did it and who did it. And we're just going to close this out for a minute and change a setting within the software. Specifically for the reports, we'll go to the MSA reports, and the MSA GRR percent based on, instead of being based on total variation, we'll change it to tolerance band. Click on apply, close this, go back into transaction, and we'll retrieve our existing transaction. Now, when we do that, we set the tolerance band to 20, whatever units we're measuring in. We look at the analysis. Again, we're still coming up with this range beyond a control limit, which is now understood what that means. But what we see now, all the calculations on the left-hand side remain the same. We're still calculating a standard deviation for each of these components. However, the comparison basis now is based on the tolerance band, which is 20, divided by 6. So 20 divided by 6 takes us into the same playing field, so that we're dealing with one standard deviation, and the tolerance divided by 6 gives us sort of a similar kind of component for the tolerance band. When we do that and we work out the arithmetic, we find that based on the tolerance band, the repeatability or equipment variation is now roughly 6% of the total tolerance band. And in a similar way for the people doing the measuring, the appraiser variation is 6.89%. The overall Gage R&R is 9.17% based on tolerance band. And the number of distinct categories, which again has nothing to do with tolerance band, it's the part-to-part standard deviation divided by the Gage repeatability standard deviation, which is taken from these calculations, is 5, approximately 5. And so in this case, based on tolerance band, the Gage R&R is acceptable, and the number of distinct categories was always acceptable. So it's another approach to doing the Gage R&R study, to use the tolerance band if you wish. And that's pretty much it. So, and if you look at the ANOVA analysis, not much changes, except down here, instead of doing it based on total variation, we're doing it on tolerance band, and we get similar results for the column now called percent of tolerance band. So that, in a nutshell, is how one does a Gage R&R within the QC Pro Gage management software. Thanks for watching.